This problem is involved a little bit more, and let's talk about the work done by the gas. Okay? So let's talk about work done by the gas. And so I would just, without even talking about the problem, let's just think about, let's talk about the work. Work is defined as minus external pressure times volume change. Okay? And then you're changing your volume from initial volume to final volume. That's the notation, the definition of the work. It is very actually kind of not, you're not so familiar with looking at this, but this is the way that it has to be done. And let me show you one of the scenarios. Okay? So you're looking at the piston. Piston is what's inside of the engine, and we are going to define the system as the gas that confined here. So, like I said, sometimes it's nice to recap what is my system. So gas confined in the piston. And I want to also mention that the number of moles of the gas is fixed. So N is fixed here. And so therefore, we also call this is a closed system. So number of mass is conserved. Anyway, you're talking about the gas. And if you think about it, gas is like a little person trying to push this wall, right? And that's a system. There are a bunch of the minions of the gas is trying to push the wall of the piston and trying to do the work. And you're moving this wall from original position to the other, and that's your delta V. But what you're pushing yourself against the external pressure. So work is done by the system is defined by external pressure, not your internal pressure. So that will be, once again, will be explained and then by you and by the lecturers, and you'll get to know. So this is a definition of the work, but there are cases that is actually this equation is very simplified when P external is constant. Okay? And we are dealing with a case here. This is a case that this is a cylinder of gas containing the piston. The volume is given, pressure is given. This is the initial pressure and the volume. And then this one is maintained to be at the constant temperature. So it's a long explanation to say this is an isothermal process. And this is your initial volume and the pressure is given. This piston is released, expands until the pressure inside of the cylinder equal to the atmospheric pressure outside, which is 1 atm. So in the beginning, you have initial pressure is 5 atmospheric pressure, and your external pressure is 1 atmospheric pressure. And your final pressure is, in the problem says, 1 atmospheric pressure. And so this one is the piston is released, gas expands until the pressure inside is equal to the outside pressure. So this gas, which is your system, their external pressure has been constant at 1 atmospheric pressure. So therefore, this is a case where we are moving the resistance, which is an external pressure that has been constant throughout the process. This one can be taken out, minus external pressure. And the final volume minus initial volume is delta V. So this expression shown up here, this one is going to be taken out, and this whole thing is a delta V with a retaining minus sign in front. So I'm going to actually put a sign minus here. So work is minus when your delta V is positive. Okay? So positive volume change, expansion, your work is negative, and that's what this looks like. Okay? So this is the notation of the convention because we are defining our system as the gas inside the cylinders. As far as the gas inside the cylinder is concerned, you are essentially exhausting yourself. And so your work is negative when you do the expansion. Okay? So that's the notation. So that's the concept. And when your external pressure is constant, and then essentially this simple equation is very useful. And this is the work in irreversible expansion or compression. It doesn't matter. But the thing is, it's not reversible. It's an irreversible expansion, essentially, because it is inside the pressure has been always higher. Okay, so but what kind of problem they say asking? Calculate the amount of the work done by the gas. Okay, and so that's and then they also mentioned that at constant temperature and 25 degrees C. And 25 degrees C, you have to immediately convert it into 298 Kelvin using adding 25 to 293. Okay. So I think that I kind of have an overview on what's going on inside, and the initial pressure is 5. I guess the initial volume was 5. No, not 5 ATM. Sorry. That is 4 ATM and 5 liters of the gas. And the final volume, we don't know, but we'll figure that out. Okay? And then they have another information that ideal gas behavior means, well, I can use PV equal nRT equation to know the relationship between pressure, volume, and the temperature. So these are all the ingredients that I have. And my goal is essentially want to figure out what is my work, which is external pressure times delta V. And the delta V is final minus initial. I guess it boils down to, for me to figure out what's my final volume, and then I can plug that in, and then I can get that answer. So from here, so let's start from solving the problem from this side. And if you have the pressure and the volume, and then what you can calculate is N, which is a pressure volume RT. Because you know the temperature is 298 Kelvin. This time temperature 298 Kelvin. It is a isothermal process. So that's what it is. So I have all the information. So all I need to do is just simply plug it in. 4, 5, 0.082, 298. And then you will get the number of 0.817 of gases. So there are 0.7 mole of gases represented by the 6 dots, and those are the gases there. And then when they expand it, I mean, you still have only 6 dots, right? Same number of moles of the gases there, right? So therefore, here, even, I want to know my final volume, which is PV and RT, and you can use your N value from the calculation from the left-hand side. So your N is still the same, so 0.817, R is 0.082, T is 298, and final pressure is 1. So that's when you can put it in. And then you will have 20.0. So my calculation is actually very simple. I think that I wanted to recap one more time. The reason that it's so simple is I kind of follow the rule, which is rule is governed by my choice of R. You know the unit of R is 0.82 atm liter per mole Kelvin. So what that means is if you want to use this value of 0.82, you are going to use pressure as an atm, volume as a liter. Okay? So does here. Because here, because I choose to use this value, so the temperature, pressure atm, and the volume must come up with the unit of liter. So that's your answer. Okay, so now this is a 20 liters. Before it's a 5 liters, so your delta V is 15 liters. So then I think that now I'm getting an answer. So therefore, work, which is the minus external pressure times delta V for irreversible expansions, which is when the external pressure is constant, I'm going to write 1 atm, 15 liter. Your answer is minus 15 atm times. This is your answer. That's your answer. And this is actually the same answer here too. Okay? If you go down, you'll see that the answer for this is minus 15 liter atm. That's your unit. So it's a good point for me to recap what this means. You know the pressure times volume, that's the unit of an energy. Have you thought about that? Pressure times volume is, pressure is force per unit area. So Newton per square meter is an example. And the volume is meter cubed. So multiply that, Newton times meters alive, that's a joule, right? So same thing here. The pressure times the volume has a unit of an energy, and that's exactly that actually we are using for your R value. And this is not a common choice for the one, so actually I took the liberty I wanted to change it to joule. Okay? I want to do that. And how should I do? You know exactly conversion factor of the atm liter to the joule, which is this. 0.082 atm liter per mole Kelvin, right? So I'm just retaining this. I'll write down everything. Mole Kelvin. This R quantity is same as 8.314 joule per mole Kelvin. This is the same quantity up and down, right? Because of that, and then I don't have to worry about this. This is the same, and then now this is a joule, atm liter, joule, atm liters are gone, so the joules is a term that survived. And then you will ended up getting this number here is minus 1.5 to the 10 to the 3 joule. That's the same as minus 1.5 kilojoule. Okay? So if you want to convert that from the atm liter, which is an energy unit, to a conventional unit choice of an energy, unit of the joule, you can use that as a conversion factor.